In this video, we are going to talk about Newton's second law in terms of linear momentum. At the beginning of the formulation of the formula, Newton has wrote his second law in terms of linear momentum, but we simplified it as the force resultant is equal to force times mass. The force resultant is equal to mass times acceleration. It is a simplified form of Newton's second law, but at the beginning it was written as the Newton's second law is equal to the time rate of change of linear momentum is the way how you define Newton's second law in terms of linear momentum. So now we are going to come across these formulas from the known Newton's second law, which is force is equal resultant is equal to mass times acceleration, and we are going to do some numerical problems. Okay, from the previous discussion, we have already defined as linear momentum as mass times velocity. Okay, so if the velocity is the linear momentum is taking the direction of the velocity, so linear momentum is a vector quantity, and its SI unit is SI unit for linear momentum, maybe Newton second or kilogram meter per second. So we did this last time. Now from Newton's second law, the resultant force is equal to mass times acceleration. But from our mechanics, the acceleration, kinematics from unit 2, the acceleration is given by how much? The v minus u, the final minus the initial, divided by the time taken, the change in the duration taken. Now, instead of acceleration, we are using v minus u over change in t. So the force resultant is equal to the mass into, instead of the acceleration, v minus velocity final minus velocity initial, divided by change in t. Okay, let's distribute the mass into the bracket. The force resultant is equal to the mass times the v minus the mass times the initial velocity, the u, divided by the change in t. Okay, but from definition of linear momentum, the mass times the v is the final momentum, and the mass times the u is the initial momentum. So the force resultant is equal to how much? The final momentum, m times v, minus the initial momentum, m times u, divided by the change in time. Oh, I'm sorry. P initial divided by the change in time. So this means this P final minus P initial is in final momentum minus initial momentum is simply the change in momentum. So the resultant force is equal to the change in P, the change in linear momentum, divided by the change in time. So this is Newton's second law in momentum form. Okay, now, but this change in P, which is the P final minus the P initial, is gonna give you another quantity called impulse, abbreviated as, it's usually represented by J. So the symbol for impulse is J. Impulse is nothing but it is the change in linear momentum. Therefore, the force resultant is how much? The force resultant is the change in P, okay, over the change in T, but the change in P is called impulse J, and divided by the change in time. So the force resultant is equal to J impulse divided by change in time. All right, now what is the expression for the change in P? For linear, the impulse, if you crisscross, the force resultant times the change in P, times the change in T is equal to the J. Okay, the J. So impulse is, you can say impulse is the product of force and resultant force and time rate, or you can say impulse is, you have two formulas for impulse. You can say impulse is what? The change in P, or P final minus P initial. Let's develop this with numerical examples. In this specific problem, we are required to calculate the initial momentum, the final momentum, P initial, P final, PF, the change in P, or it's also called actually J. We will see this later on. The impulse, the net force acting on the mass of a 2.5 kilogram ball moving with an initial velocity of 10 meters per second and bouncing off a wall with a final velocity of 8 meters per second, making a contact with the wall for 0.04 second. Let's dive in. Okay, in this specific problem, we are given the mass is 2.5 kilogram and the initial velocity is 10 meters per second. If this is a wall, so the initial velocity is towards the wall, this is the direction of u, and it bounces off with the opposite direction, meaning the final velocity is towards the negative x-axis. Now the final is 8 meters per second to the negative x-axis. The change in time is given to be 0.04. Now the first question says you are asked to find P initial. So P initial is equal to how much? So it is mass times U initial. So it is towards the positive x-axis, and this is 2.5 kilogram times 10 meters per second, 10 meters per second in this direction. So this is equal to how much? 25 kilogram dot meter per second, or this is 25 Newton meter. Yes. Okay, now what is P final and B? We are looking for P final. The P final is how much? The P final is the mass times V final. So this is equal to 2.5 kilogram times negative 8 meters per second. Okay, so negative 8 meters per second means it is in opposite direction. So the direction of the initial momentum is, so this gives you 20 kilogram meter per second in that direction. Okay, or it is 20 Newton second towards the negative x-axis direction. Okay, this is the final momentum. You can see the final momentum is smaller than the initial momentum because in the bouncing process air resistance is there, meaning the force, the system is assumed to be not isolated from forces. Instead there is some external forces, because in the presence of external forces linear momentum is not conserved. So C is asking you the change in P. So the change in P is the change in linear momentum is the P final minus the P initial. So here you are adding the P, you are doing this subtraction as a vector. Yes, so this is equal to how much? P final is negative 20 Newton second, because it's towards the negative x-axis, minus the P initial is towards the positive x-axis. So this is how much? 25 Newton second. So the change in P is how much? It is 45 Newton second negative, meaning, so the change in P, which is also called impulse. At D you are asked to get impulse. At D is impulse. The impulse is the change in P. So the answer for D and C is the same. So the impulse J is what? Is a change in P basically, is equal to, this is equal to how much? 45 Newton second in the negative x-axis direction. On E we are asked to calculate the net force. So from Newton second law in momentum form, F resultant is equal to change in P over change in T, or this is basically J over change in T. So the resultant force is equal to the J divided by the change in time. So substituting the value of J, 45 Newton second over the time is 0.04 second. So this gonna give you the resultant force is equal to 45 divided by 0.04 is 1125 Newton force is acting on the ball.